All right, so here we are. This is section 8.3, and section 8.3 is gonna, what is it gonna be? It is going to be the section that takes this idea of permutations, combinations, counting principles, and turns them into probability problems. So in section 8.3, we're gonna do probability applications, accounting principles. So we're gonna take that combination and permutation stuff that we worked on in the last couple sections. We're gonna say, let's make it work. Let's make this be a problem where we find the probability of something occurring using those counting principles. All right, so we're going to take a look at our first example here, and we're going to see whether it's a combination, a permutation, or a multiplication problem to make this thing work. Here we go. A basket contains 7 red apples and 4 yellow apples. A sample of 3 apples is drawn. Find the probability the sample contains the following. And so our options are all red apples, all yellow apples, 2 red and 1 yellow, or 2 yellow and 1 red, or more red than yellow apples. So I'll start with the first one, all red apples. So my job is to find the probability of 3 red apples. Okay. I know it's going to be a fraction, and then my numerator is going to contain the number of elements in the event that I care about. My denominator is going to contain the number of elements in the sample space, or in this case, my numerator is going to be the number of ways to pick 3 red apples, and my denominator is going to be the number of ways to just pick 3 apples, where I don't care about the color. Okay. All right, so I'm going to find E first, right? The number of elements in E, my numerator, is going to be the number of ways to pick 3 red apples. Well, there are 7 red apples in the, I don't want that. There are 7 red apples in the bowl. Right. And so I am going to take that set and create a subset from it of 3 apples, because that's how many I'm picking. I can't repeat, because once I pick an apple, it's in there. And the order doesn't matter, so that's a combination. So this is going to be a combination of 7, choose 3. Then I'm going to grab my calculator and find out what that is. 7 math combinations, 3. That's 35. So I know that my numerator is going to be 35. And now I'll find the number of elements in my sample space, my denominator. Okay? Well, if there are 7 red apples and 4 yellow apples in there, that means that there's 11 apples, and I just want 3 of them. And so then I'm going to go and say 11 math NCR3. So there's 165 ways. So then the probability, so that's going to be my denominator. So then the probability that we will pick 3 red is going to be 35 over 165. So 35 divided by 165, math, enter, enter, that's 7/33. So I have a probability of 7/33, 7 out of 33, of picking all red apples. All right, that's number 1. Let's take a look at number 2. Number 2 says they're all going to be yellow apples. So the probability of 3 yellow apples, well, that's going to be the number of ways to pick 3 yellow over the number of ways to pick 3 apples. Now I happen to already know the denominator because I already figured it out. There's 165. My numerator needs to be C4, 3. Using the same logic I used up here for 7/3. I'm just doing 4/3 because there's only 4 yellow apples to choose from. I go to my calculator and figure that out, but I happen to know that that's 4. So that's going to be 4 out of 165. So 4 divided by 165, enter, math, turn that into a fraction. Nope, doesn't reduce, 4 out of 165. Well, this isn't too bad. I got a handle on this. I think I understand what's going on here. Let's try number 3. Probability of 2 yellow and 1 red. Well, I know it's going to be the number of ways of 2 Y's and 1 R over the number of ways of 3 A's, 3 apples. I know the denominator is 165. What I don't know is, how do I find that numerator? Okay. Well, the key is in the word and. Oops, I don't want that. I wanted a highlighter. The key is in the word and. I'll try that again. All right. 2 yellow and 1 red means find the number of ways to do 2 yellow, find the number of ways to do 1 red, and then use the multiplication principle to call this M1 and call this M2 and then multiply them together. So how many ways are there to pick 2 yellow? Well, that's going to be 4 choose 2, which happens to be 6. And red is going to be, what is it, 7 choose 1, which happens to be 7. So then 4 choose 2 times 7 choose 1 is going to be 7 times 6, or 42. And so I got 42 out of 165. So 42 divided by 165, 14/55. So I don't know if you caught it or not, so I'll say it again. What we did there is we made use of both combinations and the multiplication principle, because I said this was step 1 or event 1, 6 ways to do it, and this was step 2 or M2, 7 ways to do it. And then the multiplication principle says if you know how many ways there are to do step 1 and how many ways there are to do step 2, then the whole thing is just step 1 times step 2, or in this case 6 times 7. All right, we're almost done. We still have to do number 4, more red than yellow. What does more red than yellow mean? Well, more red than yellow means, well, if there's 3 apples, if they're more red than yellow, that would mean 2 red and 1 yellow, or all 3 red. That's the only way to have more red than yellow. Or that means I'm going to add these 2 things together once I figure them out. Do I know 2? I know 3 red. 3 red was 35 out of 165 because I figured that out in the first step. 2 yellow and 1 red, well, that's pretty much what we just did, so I kind of know what to do with that. That's going to be 7 choose 2 times 4 choose 1. 7 choose 2 is 21. 4 choose 1 is 4. I think 7 choose 2 is 21. Let me check that real quick. 7 math combination. 7 choose 2. 21. 20. Okay, 21 times 4 is 84. And so I've got 84 over $1.65. That's going to give me my 2 red, 1 yellow. 35 over $1.65. That's going to give me my 3 red. So the probability of more red than yellow is going to be the sum of those 2. So I'm going to need a calculator for that because my brain isn't working like it used to. Let's see, 84 plus 35 is 119. So 119 out of 165. 119 out of 165, let's see, 119 divided by 165, math. Make it into a fraction. Doesn't reduce, so there we go. There's our probability. All right, now that was a lot. That was a big chunk to swallow, but basically what we're doing is we're going back to our definition for probability, where it's the event that you want to have happen in the numerator, the sample space in the denominator, but how we find those things gets more complicated because the examples are more complicated. The problems are more challenging. Okay. Let's take a look at another one. After studying all night for a final exam, a bleary-eyed student randomly grabs 2 socks from a drawer containing 9 black socks, 6 brown socks, and 2 blue socks, all mixed together. What is the probability that she grabs a matched pair of socks? All right, so what are they asking us to do? They're asking us to find the probability that the socks match. Well, what does that mean? That means we're looking for the probability of 2 black socks or 2 brown socks or 2 blue socks. All right. So it's 2 black. Oh, okay, I know what to do then. I'm going to find the probability of 2 black and add that to the probability of 2 brown and add that to the probability of 2 blue. Now you might be wondering, why can we just add like this? You did this before, but why? Well, remember the union rule? The union rule said the probability of A union B was equal to the probability of A plus the probability of B minus the probability of A intersection B. We're making use of that. We're just ignoring this piece right here because we can. We can ignore that intersection when our events are disjoint. And 2 black socks does not have any intersection with 2 brown socks, nor does it have any intersection with 2 blue socks. So we can just ignore those intersection parts of this and just find the individual events and add them all up. All right. I know these are all going to be fractions, and I know the denominators are all going to be the same because there are 17 socks in that drawer. 9 black, 6 brown, and 2 blue, so that's 17 socks. So this is all going to be over C 17 2, C 17 2, and C 17 2. Because there's 17 socks, and we want to pick any 2 of them. That's going to be our sample space. So 17, pick any 2 of them. That's our sample space. Over 136. Now my numerators are going to change based on what I'm doing here. Okay, so my first probability is the 2 black socks. So that's going to be a combination of 9 choose 2, which happens to be 36. And then my second one's going to be 2 brown socks. Well, there are 6 brown socks, so that's going to be a combination of 6 choose 2, and that's 15. And then my third one is 2 blue socks, so that's a combination of 2 choose 2, and there's only one way to do that, so that's 1. And so I have 36 plus 15 plus 1. 36 and 15 is 40, 51, 52 total. And so I get 52 out of $1.36. I'll make that into a fraction. I think that's going to reduce a little bit. Yep. And I get 13/34. About a 38% chance. So if I just reach into this drawer and grab 2 socks, I got about a 38% chance of the socks matching. Here's a bigger question though. What's going on there? Why do you have an odd number of socks? You lose the socks, throw that all the way too. You got like random unmatched socks in this drawer. As someone who requires that their socks be paired up nicely, that the thought of a random drawer just full of socks freaks me out. All right, we're at 13 minutes. Let's keep moving. A total of 44 people served as president through the year 2019. There were actually one person served twice out of order, so that's why, even though technically we've had 46 presidents, we've only actually had 45 different presidents. Up through the year 2019, there were only 44 different presidents. All right, so what I'd like to do is I would like to set up the probability question that if 44 people were selected at random, at least 2 have the same birthday. So this is a classic problem. It's a classic problem about if you get a bunch of people together in a room, what's the probability that some pair in that room will have the same birthday? And it's really kind of fascinating because the way that it works is you can't calculate it directly. We have to calculate it using the complement. So you remember this rule? the probability of an event is equal to 1 minus the probability of its complement. So what we're going to look at is we're going to say the probability that 2 match is going to be equal to 1 minus the probability that no match. Right? Because the reason I'm saying this is complements is it's not actually 2, it's at least 2. So it's 2 or more. Because technically, I guess in theory, you could get a room of 44 people and they could all have the same birthday. Unlikely, but it could. And so what we're going to do is we're going to set this problem up using the complement. All right, so here's how it's going to look. You ready? The probability of no people matching is going to be, let's see, what is that going to be? Well, let's do a simpler example. If I have 2 people in a room, what's the probability that they don't have the same birthday? So first person has birthday, we'll call it birthday 1 or not birthday, right? So over here is birthday, and either it matches the second person in the room, or it doesn't match, right? With the birthday 1 over here. There is a 1 out of 365 probability that it will match. There is a 364 out of 365 probability that it won't match, right? Let's say a third person enters the room. Well, there are chances that this person's birthday could match that person's birthday, or could match that person's birthday, and I don't know how to assign probabilities to these branches up here, because each of these would require that it match maybe the first person or match maybe the second person. But what I do know is there are 363 out of 365 ways that it won't match. And if I add another person, a fourth person, there's going to be lots of things up here that I don't know, but I know this. I know there'll be a 362 out of 365 chance that it won't match. And so if I have 44 branches, there's going to be a branch down here on the bottom that goes all the way down that's going to have all of those don't matches in it. And if I take 1 minus my don't matches, I'll have my 2 or more match. So what is that branch going to look like? Well, when there were 2 people, it was this. When there were 3 people, it was this times this. When there were 4 people, it was this one times this one times this one. So it looks like that denominator is going to be 365 every single time, and it's going to be to the 43rd. Now, where did 43 come from? Why isn't it 44 if there's 44 people in the room? Well, when there were 2 people in the room, there was 1 365. When there were 3 people in the room, there were 2 365s. For 4 people in the room, there were 3 300. So it looks like it's always 1 less. And then what's the numerator? Well, it's going to be 364 times 363 times ... all the way down. And when's it going to stop? Well, it started at 364, and then it goes down 1. So this number is 364 minus 1 minus 2 minus 3, 4, 5, 6, 7. So this number right here on the end is going to be 365 minus 44, 321. Now, luckily for me, I recognize another pattern here. I don't know if you recognize it or not. I'm hoping you did. Remember back when we did permutations? And we said like this, P 10, 3 meant 10 times 9 times 8 when the math was done. Right? The formula would say to do 10 factorial over 10 minus 3 factorial, which gave us 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And then 7 times 6 times 5 times 4 times 3 times 2 times 1. And those would all cancel. And we would just get the 10, 9, 8. So that means that my numerator is P 364, comma, 44. My denominator is 365 to the 43rd. Whoops, I got a small mistake there. That's 43rd. And the reason it's 43rd is I want that 44th one there. I want the 43rd one up through the 43rd one. Okay? All right. Now there's a shortcut for this formula. There's a shortcut for the formula. The shortcut for the formula is the probability of no matching is going to be 1 minus the permutations of 365, comma, n divided by 365 to the n, where n is the number of people in the room. Now I know what you're thinking. How come this formula has n here, which you said was 44, but your explanation up here had 43? All right, so here's the reasoning. That first person, if I add in that first person, there is a 100% chance that their birthday matches, which adds into this calculation here a 365 over a 365, which is that 44th one in there. Right? Now this calculation right here is going to give us the probability that we have no matching birthday. So I'm going to go ahead and grab my calculator and see if I can figure this out. Let's see. I want to do 1 minus a fraction where my numerator is 365, permutation 44, and my denominator is 365 raised to the 44th. I'll press enter and I get overflow. What on earth does that mean? Well, that just simply means that the calculation is actually too big for my calculator. It can't handle this problem. The math is too big. I need something more powerful. I'm going to have to go online and find a bigger calculator. So I'm going to go to Wolfram Alpha, and I'm going to use their computational intelligence. All right, so what do I want to calculate? I want to calculate 1 minus the permutation of 365, comma, 44 divided by 365 raised to the 44th. That looks right. There's my exact result. I don't even want to attempt to try to read what that number is. I'll enlarge it. My decimal approximation is 0.9328, and tell me how many digits you want and I'll get them for you. So it looks like there's about a 93% chance. So if I go back over here, what I'm going to say is that the probability of 2 plus matching is approximately 93%. We have about a 93% chance that 2 or more people in this room will have the same birthday. Now, this is one of those examples of probability that just seems crazy. There's 365 days in the year, 44 people. There should be a chance. There should be a really good chance that if you got 44 people together in a room, they wouldn't have the same birthday, that 2 or more wouldn't have the same birthday. Turns out, the way the math works is counterintuitive, and it ends up being quite probable that 2 or more have had the same birthday. And actually, there have been 2 presidents that had the same birthday. I forget who it is now offhand. I'd have to look it up, but there have been 2 presidents with the same birthday. All right, I'm going to call this one here. There's still a whole bunch more. I'll come back and we'll do some more examples in the next video.